Hi everyone, my name is Sneha Jos, and I'm a physics major, and today I'm going to be presenting my Keystone project, which I'm also working on for a senior thesis. So for my project, I am simulating a beam decelerator to improve anion cooling experiments, eventually to be used in antimatter gravity experiments. And I know these are a lot of words, but as we go through the presentation, I'll break it down and hopefully it'll make more sense towards the end. So first, what is antimatter? Antimatter is has the same mass but opposite charge as subatomic particles. So if you have a proton which has a positive charge, you have an antiproton, which is a negative charge, and they both have the same mass. So why do we care about antimatter? We can no longer find antimatter in the natural world, and if we want antimatter, we have to make it. And lies at the heart of one of the greatest mysteries in physics, because right after the Big Bang, all our laws of physics point to there being equal amounts of matter and antimatter in the universe. But then something happened, causing an imbalance between matter and antimatter. And when matter and antimatter come into contact with each other, they annihilate. So if there wasn't this imbalance, none of our natural world would exist because it all would have annihilated each other. So something happened that caused slightly more matter than antimatter. And one of the greatest mysteries in physics is what happened. So scientists are investigating any potential differences between matter and antimatter, and one of the main characteristics they're investigating is how gravity affects matter and antimatter differently, and this leads to anti-hydrogen gravity experiments. So anti-hydrogen is composed of one anti-electron, which we call a positron, and one antiproton, and they bond together to create anti-hydrogen. This system is used because it's the easiest neutral system of antimatter to make, and at CERN, they are investigating how gravity affects them. This research is only done at CERN, which is the world's biggest particle physics laboratory. And last year, I had the privilege of doing 8 months of study abroad in Geneva, and I was able to be at CERN and do this research in person, which I'm super grateful for. So only CERN has the capability of making anti-hydrogen, and in order to make anti-hydrogen and use it for precise measurements, we need the anti-hydrogen to be cold, because if it's not cold, it's going to be moving around a lot, and we won't be able to detect anything new. So we need the cold anti-hydrogen for precision measurements. And the only way to get the anti-hydrogen cold enough in order to make good measurements is a process called laser cooling. And I know laser cooling sounds like kind of an oxymoron because lasers make things hot. And I don't really have time to get into the process of laser cooling, but if anyone has questions, I can elaborate more on the Q&A. It's a super cool process. So there's a couple ways to get this cold anti-hydrogen, but the way that's being used in the experiment I'm working on is cooling the antiprotons used to create the cold anti-hydrogen. So at CERN, the experiment receives hot antiprotons, and what we're aiming to do is mix them with laser-cooled anions, because it's hard to laser cool antiprotons directly. And anions are just negative ions. So if we have hot antiprotons and laser-cooled anions, we can mix them together, and they will cool each other in a process known as sympathetic cooling. So this will cool the antiprotons, and then they can then be used to make cold antihydrogen. The only problem is anions have never been laser-cooled before. Laser cooling is a common experimental method for positive and neutral molecules, but due to their structure, anions have never been laser cooled before. So my experiment, the Borealis experiment, has theoretically determined that carbon-2- can theoretically be laser cooled, and decided to make a physical apparatus dedicated to trying to laser cool them. So this is the apparatus. I know there's a lot here, but my main focus is right here at the deceleration tube. We need to decelerate the particles because in order for them to be laser cooled, they need to be trapped so they can be still. So we have an ion trap here. And you can think of the ion trap as a valley or a bucket. And this ion trap has a specific depth and specific energy depth. So in order for all the majority amount of particles to be trapped, they all have to be within this depth. So not only do they have to be slow enough, but their energy spread has to be narrow enough so that it fits into this bucket or trap. So this is where my work comes in. So I'm simulating something called a pulse deceleration tube. The current deceleration tube used at the Borealis experiment that I showed previously is not pulse and doesn't do anything to compress the kinetic energy spread of the beam. It only slows down the particles, and this results in a lot of particles being lost in the process of getting them into the particle trap. So my project is simulating a pulse deceleration tube that has a unique geometry, which you can see the serrated crown structure is not commonly used in deceleration tubes. So this unique geometry compresses the kinetic energy spread, and we also change the voltage from a certain threshold down to 0 in order to pulse the kinetic energy. So my methods were simulating this in a software called COMSOL, which is a finite element analysis software, which just means it calculates complicated electric fields and other complicated math. So I built this geometry into COMSOL, and these are all images from my simulations. So I built the geometry into COMSOL, and then first I calculated the electric field, and then I simulate a beam through, which just means the software is simulating the forces, is simulating how the electric field affects the particles, and we get these images of beams going through. So for my results, I effectively showed that the pulse deceleration tube does compress the kinetic energy of a beam well. So here, this is one of the beams I use. So we start with the kinetic energy spread of around 1800 eV, and then we compress it to a kinetic energy spread about 1.5 eV. eV is a unit of energy, electron volts. And we also slow the beam down. Here the average is about 1700, and here the average is about less than 1 eV. So I was successful in simulating this pulse deceleration tube and showing that it's more effective than the current Borealis tube. I also found that this lens, by applying the different voltages to each electrode, this tube can also be used as a lens. So if we choose the combination of electrodes just right, we can see that the beam gets more collimated and easier to enter the tube. So this also helps with particle loss. Yeah, thank you.
All right, we'll move on to the questions section.
Hi, hi, great presentation. My question was, what do you mean by hot proton versus a normal temperature proton? And could you elaborate on the laser cooling process?
Okay. Yeah. So when I say hot, I mean high energy because we kind of use those in conjunction with each other. So CERN creates the antiprotons by basically hitting protons really hard into a metal sheet, and that creates antiprotons, and they're super high energy. So the apparatus at CERN already has things in place to slow them down a little, but it's still too hot or too high energy for us to be able to do any sort of precise measurements on them. As for laser cooling, it involves utilizing the Doppler shift. So when particles are moving fast, you send a laser to them, and they see the laser as a different wavelength because of Doppler shift, like red shift, blue shift, and they see the particles at a different wavelength. And because of this, when they run into each other, the proton loses some sort of energy. And since they have to be, because of conservation of momentum, the particle that you're laser cooling has to slow down.
Great work, Sneha. In terms of the implementation of your design,
Yes.
where are you in that pipeline?
So since I'm no longer at the Borealis experiment, this was kind of an investigation of the pulse deceleration tube itself. The work I'm not sure if it'll be implemented at Borealis, but I still think it's useful work because pulse deceleration, slowing particles is useful in a bunch of experiments and in many precise experiments. So even if it's not implemented at Borealis, I think it's a useful investigation of how particle decelerating works.
Thank you.